A roller compactor is common on all job sites. This type of machinery compacts engineered fill to enhance soil characteristics. This is vital for solidifying a foundation or roadway. A roller compactor densifies soil by expelling the air voids and even rearranging soil particles into a denser condition. The question lies, has the soil been compacted enough? The standard and modified Proctor determine the maximum dry density and optimum moisture content of soils. This quantifies a soil's most dense state. Field methods that measure dry density and water content, such as the sand cone, nuclear density gauge, and drive sleeve, are capable of measuring density in situ. The field values are always compared to the lab value, maximum dry density, and optimum moisture content to ensure adequate compaction and moisture. The end result of the test should look something like this. This is known as a Proctor curve. The maximum dry density and optimum moisture content can be extrapolated from this plot. First, we will select a range of moisture contents that bracket the optimum and moisturize the soil in individual portions. Then compact the specimens one by one into a mold of known volume. By weighing the molded soil, a wet density can be obtained. By drying the compacted sample, a moisture content can be obtained. Finally, with these two pieces of information, a dry density can be calculated. Each point on the graph represents a dry density and a moisture content. A line is made through the data set, and the optimum and maximum can be read off. A standard Proctor curve that is representative of engineered fill should always be used when compacting roadways, foundations, embankments, landfill liners, and many more geotechnical applications. The density of engineered fill influences shear strength, compressibility, and permeability of soils. We will start by describing the various methods of the standard Proctor. Method A and B require the same procedure and set of tools, whereas Method C is quite different. The method solely depends on soil type. Most engineered fills fall within the Method A and B range, whereas larger aggregate base course and crusher run will entail using Method C. Method A can be used if 25% or less by material weight is retained on the number 4 sieve. Similarly, Method B can be used if 30% or less by material weight is retained on the 3/8 inch sieve. If this gradation requirement is not met, we must refer to Method C. Method C may be used if 30% or less by mass of the material is retained on the 3/4 inch sieve. If more than 30% of the material is retained on the 3/4 inch sieve, there is no ASTM for this material. Proctor values can be difficult to find due to voids. Please refer to the Army Corps of Engineers publications on such matter. Method A and B require the 4-inch mold, a 5.5 pound hammer with a drop height of 12 inches, 3 layers, and 25 blows per layer. Method C requires the 6-inch mold, the 5.5 pound hammer with a drop height of 12 inches, 5 layers, with 56 blows per layer. Here are the tools. First, we have the modified hammer, the modified mold 6-inch, the standard hammer, standard mold 4-inch. We have a scoop and a number 4 sieve and a pan. The wet sieving method is preferred by the ASTM standard, so we will be sieving a material brought in from the field as is. Since our material is generally classified as a clay fine to medium sand, we will be using the number 4 sieve. Therefore, Method A. If the gravel content were higher in our test specimen, we would have used the 3/8 inch sieve. First, we sieve the whole sample and keep what has been retained and what passes. Sieve at least 20 pounds of material, for it will later be subdivided. That is, at least 20 pounds must pass the sieve and be kept for testing. After sieving the whole sample, weigh the amount that was retained on the specified sieve. This mass will be used to calculate the oversized fraction, also known as coarse fraction. This portion will not be used during the test. Next, weigh the passing amount. This mass will be used to calculate the test fraction, also known as finer fraction. This portion will be used during the compaction test. Oversize and finer fraction. Oven dry the portion retained on the number 4 sieve. Weigh this amount. Also remove a representative portion of the passing amount and also oven dry. Calculate the oven dry total mass based on the moisture content from that portion. Now the oversize and finer fraction are ready to be calculated based on the oven dry weights. We will now calculate our coarse fraction and finer fraction. The amount retained totaled to 1371.66 grams. Divided by the total sample weight gave us a coarse fraction of 11%. We now know that method A is applicable to our soil since less than 25% of our material by weight was retained on the number 4. The finer fraction is calculated in a similar fashion. Therefore, 89% of our sample is available for use. After mixing the finer fraction thoroughly, weigh out approximately 5 representative pounds in a bowl. Tare the bowl and transfer 5 pounds into it. Repeat this step 3 more times to obtain 4 subspecimens, all containing even amounts of soil. Estimate the general water content of your soil by squeezing a small amount. The goal is to bracket the estimated water content within the 4 trials. Select the molding water contents for the subspecimens such that 2 subspecimens are dry of optimum and 2 subspecimens are wet of optimum. Molding water content should vary by less than 2%. Generally for a 5-pound sample, this means that the increment should be 50 milliliters. Since our specimen was fairly dry, we added 100 milliliters to our first, 150 milliliters to our second, and so on. Thoroughly mix each subspecimen with a scoop. Do not mix by hand because water can adhere to the palms of the hand, taking away from the moisture content of the subspecimen. Mix until each subspecimen is consistent and has the same color throughout. Refer to Table 2 of the ASTM standard for standing time of moisturized specimens. Since our soil is a well-graded sand with fair amounts of clay, our standing or moisturizing time is 16 hours. Cover the soil adequately and allow soaking to occur for the specified amount of time. First, weigh and record the mass of the mold. Be sure and weigh the mold without the collar attached to it. Uncover the first subspecimen and mix thoroughly. Put the collar on the mold and scoop soil into the mold. Fill the mold 1/3 to halfway up the body for the first lift of soil. Take the standard hammer and begin lifting and dropping freely in the rotation manner specified in the ASTM standard. The first 4 hammer strokes should be in a cross pattern. For the remaining 21 strokes, continue in a circular manner. Count 25 hammer strokes and stop. Remove the hammer from the mold and add another lift of soil and repeat, totaling to another 25 hammer strokes. Repeat again so that 3 lifts have been achieved. After the 3rd lift, the soil should be at a level above the top of the mold if it did not have its collar on. Carefully unscrew the wing nuts and rotate the collar back and forth, being careful not to shear any soil off. Remove the collar, place the straight edge against the top of the mold and begin a sawing motion, cutting any soil that has been compacted above the top of the mold. Clean off the top of the mold, ensuring that the soil is flush with the top. Brush all sides of the mold. Be sure no soil was stuck onto the bottom of the mold during the hammering process. Once the outside of the mold is completely clear of any soil, weigh the soil and mold. Record this value. Weigh and record the mass of a tare in the process. for we will obtain a moisture content of the material that we just compacted. Use a hydraulic jack or hammer to extract the soil within the mold. The most consistent moisture contents come from weighing the whole pill. Once the soil is extracted, break it apart so that the material can fully dry. Transfer the soil into the tare. Weigh the material and tare and record this value. Place the moisture content sample in the oven to dry at 110 degrees Celsius. Repeat this procedure for the remaining subspecimens. For the points that are dry of optimum, notice that the soil does not easily compact and hammering seems to not do a lot. For the points close to the optimum moisture content, notice that the soil compacts easily under hammer strokes. For the points wet of optimum, notice how the hammer sinks and sticks into the sample, making it difficult to remove. Be sure and be consistent for all points and allow sufficient time for moisture content samples to dry. After all samples have sufficiently dried, remove all subspecimens from the oven and allow them to cool. Weigh the tares and record the weight of the tare plus dry soil. The standard Proctor curve can now be generated from the recorded data. Here are our Proctor points, listed on the left-hand side column. We ended up doing 2 extra points to ensure our last 2 points were wet of optimum. 5 points is actually preferred by the ASTM standard. Next column we have our tare ID, tare weight, then wet soil plus tare, dry soil plus tare, and finally calculated moisture content. This sheet pertains only to the moisture content portion of the test. The next slide will display wet density and dry density data. Since the standard Proctor mold is a known volume of 0.0333 cubic feet and we have a known weight, we can easily calculate what is known as the wet density. From the moisture content, the dry density can be tabulated. Finally, the zero air voids line can be calculated based on the specific gravity of the soil. The zero air voids line will be plotted on the Proctor curve. This is a theoretical line that displays the soil's dry density if the soil had no air voids. We will look at the first row as an example for our sample calculations. First, we will calculate the moisture content. We have the mass of the water divided by the mass of the soil, that is the dry soil alone. On the numerator, we have wet soil plus the tare minus dry soil plus the tare, gives us just the water. In the denominator, we have the dry soil plus the tare minus the tare weight, which will give us just the dry soil. Our first row moisture comes out to 4.4% once we do these calculations. Next, we will calculate the wet density. With our known volume of our mold, we divide the wet weight of the compacted soil by the known volume. Multiply this by a conversion factor so that our final units are in pounds per cubic foot. After performing these calculations, our wet density came out to 119.4 pounds per cubic foot for the first subspecimen. With a wet density and a moisture content, we can easily calculate what is known as the dry density. The dry density is the density of the soil if it had no moisture. To do this, we divide the wet density by 1 plus the water content in decimal form. Notice that the dry density is less than the wet density. This calculation essentially subtracts the water from the compacted subspecimen. The wet density is not a good indicator of the relative density of the soil, for wet densities can be high along with very high moisture contents. Once a high wet density is divided by 1 plus a high water content, the dry density may not yield a high value relative to others. In our case, the dry density of the first point came to 114.4 pounds per cubic foot. Next, we calculate the density of the subspecimen if it had no air voids, also known as the zero air voids density. The specific gravity is multiplied by the unit weight of water, then this value is divided by 1 plus the water content in decimal form times the specific gravity. In this case, the zero air void's density came to 150.6 pounds per cubic foot. Here's our standard Proctor curve. The 6 calculated dry densities are plotted against their respective moisture contents. This yields a curve that should look somewhat symmetric about the optimum and maximum. In our case, the maximum dry density came to 123.5 pounds per cubic foot at an optimum moisture content of 9%. Theoretically, if we were to moisturize our soil to a consistent 9% and compact it to its most dense state in the field, test results should yield something close to 123.5 pounds per cubic foot as a dry density. Notice the zero air voids line to the right of our curve. As the moisture content of our compacted subspecimen is increased, the air voids decrease since the Proctor curve gets closer to this theoretical line. But water is a somewhat incompressible material, therefore lower densities are achieved once the maximum has been exceeded. To find our relative density or percent compaction, we always compare to our maximum dry density achieved in the lab. If we were to go on a job site and measure the density in the field of a similar material, we could calculate its percent compaction. Also, if we had the in situ moisture content of the field material, we would know whether it is too dry, too wet, or just right. Many job specifications will indicate structural fill has to be compacted to a certain degree. This is what they mean. If a roadway subgrade has to be compacted to 98% of its standard Proctor, then this equation should yield 98% or greater to meet specification. Also, moisture contents are normally specified. Specifications should indicate whether compacted fill can be within plus or minus 2% or plus or minus 3% of optimum moisture content. Various methods for the modified Proctor, ASTM 1557. Method A. Method A may be used if 25% of the sample by weight is retained on number 4. Oversized fraction must be applied if 5 to 25% of the material is retained on the number 4. If the gradation requirement of method A cannot be met, then refer to methods B and C, B being first. Method B may be used if 25% or less by mass of the material is retained on a 3/8 sieve. If 5 to 25% of the material is retained on a 3/8 sieve, we must also apply an oversized fraction. If the gradation requirement for method B is still not met, then we must refer to method C. Method C may be used if 30% or less by mass is retained on a 3/4 sieve. This mostly pertains to mixtures of natural and processed soils or aggregates such as gravel or crushed rock. The methods for A and B are the same, whereas C is different. Methods A and B require the 4-inch mold, the 10-pound hammer with a drop height of 18 inches, 5 layers, 25 blows per layer. Method C requires the 6-inch mold, 10-pound hammer, 18-inch drop height, 5 layers, and 56 blows. Here's an aggregate base course sample. It is considered crusher run or crushed aggregate. This type of material is mainly used for directly beneath large-scale roadways with an asphalt or concrete covering. Here method C will be used since the gradation requirement for method B was not met and approximately 23% of the material by mass was retained on a 3/4 sieve. Weigh and record the mass of the 6-inch mold. Be sure to weigh the mold without the collar on. Approximately 12 pounds is weighed for each subspecimen, and 100 milliliters of water are added incrementally between points. The sample is then mixed thoroughly and covered for 3 hours. After 3 hours, the sample is ready for compaction. Scoop the material into the 6-inch mold until at least 1/5 of the mold is covered with the material. The 6-inch mold is used to ensure larger aggregates can be compacted into the mix. The hammer rotations are a bit different from the standard Proctor. The rotations are still in a cross pattern, but the diagonals must also be crossed. After the 9th blow, proceed in a circular manner until the 56th blow. Repeat the process 4 more times, totaling to 5 lifts. After the last lift has been compacted, ensure that the soil level has risen above the top of the mold if the collar were not on. Unscrew the wing nuts and carefully remove the collar. Use a straight edge to smooth the top of the surface of the mold. Weigh and record the weight of the mold plus wet soil. Also weigh a tear in the process. Jack or use a hammer to remove wet soil. Place the soil in the tear for a moisture content determination. Weigh and record the mass of the tear plus wet soil. Place the full tear in the oven to dry at 110 degrees Celsius. Repeat this process for the remaining Proctor points. The wet density calculation for the modified Proctor is the same, except the volume of the mold is twice that of the standard mold. The table shown here displays this result. The standard mold is 1/30th of a cubic foot, whereas the modified mold is 1/15th of a cubic foot. The moisture content determination and dry density calculation do not differ from the standard. Here are the results of the modified Proctor moisture determinations. Notice the optimum moisture content is at a much lower value. This is due to the difference in material. The crushed rock particles are larger than the clay sand and become saturated at lower moisture contents. Smaller particles have more surface area and therefore need more moisture to become saturated. Here are the results to the modified Proctor wet densities and dry densities. The dry density values are much larger due to the increased unit weight of the crushed rock and stone in the mix. After calculating the wet densities, the dry densities are found by dividing the wet density by 1 plus its respective moisture content for that trial. Dry density is again plotted as a function of moisture content. In this case, our stone-based material yielded a maximum dry density of 141 pounds per cubic foot at an optimum moisture content of 5%. This concludes the standard and modified Proctor test procedures and data reduction sections.